good evening, ladies and gentlemen, and welcome to our second virtual SETI Talks. This is the monthly lecture series produced by the SETI Institute in Mountain View, California. My name is Bill Diamond. I'm the president and CEO of the SETI Institute. We're a 501c3 nonprofit research and education institution whose mission is to seek out life beyond Earth and understand and explain its nature, origins, and evolution. Like people all around the world, we're currently doing this work from home, but our science, education, and outreach continue. And by the way, happy Earth Day 2020. Under the circumstances, perhaps we're compelled to ask if our own planet has somehow hit the reset button. The coronavirus is forcing us all to rethink how we live and work and function in a highly constrained environment. Tonight's virtual presentation is another example of how all kinds of organizations are leveraging the tools and technologies we're already familiar with to overcome obstacles and stay mission focused. Our SETI Talk series is usually presented live at SRI International in Menlo Park, California, just up the street here, and very close to the SETI Institute's headquarters. Each lecture or panel discussion is video recorded, and they live on through our SETI Talks YouTube channel. So I encourage you to visit that YouTube channel and see all the past lectures that have been part of this series. In our live presentations, I always ask the question, how many are attending a talk for the very first time? So I'd like to continue that tradition and ask you to let us know if this is your first SETI Talks experience. You'll soon see a pop-up window that should appear on your screen where you can let us know. Select the answer that fits and hit the submit button, and we'll share the answer with you later on. So one advantage of a virtual platform is that we can reach a much larger audience anywhere and everywhere in the world. So use the chat feature in Zoom, you'll see that at the bottom of your screen, to tell us where you're joining from. We love to know. It's always fun to see how far and wide these talks reach, so please let us know. And of course, you'll have the opportunity to ask questions during the talk that will be addressed at the end of the formal session, and you use the Q&A feature that you'll also see at the bottom of the screen to ask questions that you want to be addressed by our panelists. So tonight we examine one of the newest and most intriguing discoveries in modern astronomy. That is a phenomena of so-called fast radio bursts, or FRBs. These are extremely energetic but very short bursts of energy that we observe in the radio spectrum and don't fully understand, but perhaps we're getting closer. Leading our moderated panel discussion tonight is Dr. Jill Tarter, who really needs no introduction, but for some of you who may not be familiar, let me say a few words about her. Jill is one of the co-founders of the SETI Institute, together with Frank Drake and Carl Sagan, back in 1984. She's currently the Emeritus Chair of SETI Research at the Institute and serves on our Board of Trustees. Jill studied engineering physics at Cornell University as an undergraduate and received both master's and PhDs in astronomy from UC Berkeley here in Northern California. Jill is one of the pioneers of SETI research and has devoted much of her professional life to answering the question, are we alone in the universe, by searching for evidence of technological civilizations beyond Earth. She served as project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories around the world. She's a fellow of the American Association for the Advancement of Science, the California Academy of Sciences, and the Explorers Club. She was named one of Time Magazine's 100 most influential people in the world in 2004. And one of the Time 25 in space in 2012. She received a TED Prize in 2009, 2 public service awards from NASA, multiple awards for communicating science to the public, and has been honored as a woman in technology. She's an adjunct professor in the Department of Physics and Astronomy at USC, and asteroid 74824 Tarter 1999 TJ16 has been named in her honor. And for those of you familiar with the movie Contact, Jill served as the inspiration for the character Ellie, played by Jodie Foster in that movie. And it's fair to say that Contact as a movie also served as inspiration to so many young people and so many young astronomers and astrobiologists that are with us today, both men and women, now at the SETI Institute and other institutions around the world. So with that, let me turn the podium over to Jill, who will introduce tonight's panelists and get us going. Jill.
Thank you, Bill. I thought there was going to be a slide coming up, but that's fine. I have a tantalizing slide for a background because I was trying to make the point about how hard it is to imagine or focus or discover something that you can't understand there, right? And I was pointing out that this is life as we don't yet know it behind me, but Aboriginal artists had no problem with doing this kind of imagine what you don't yet know. And I think FRBs have a little bit of that same, fast radio bursts, FRBs have a little bit of that same kind of aspect to them. Tonight, we're going to have a couple of lightning talks from our two guests, Wael Farah and Daniele Micheli. And then we will do some conversation and I will ask some questions and then it'll be your turn. We will have collected and organized the questions that you've submitted, and that's how we'll end the hour. So first, Wael Farah completed his bachelor's degree in physics and his master's in astrophysics in his home country of Lebanon. Before he left to go to Australia in 2016 to do his PhD in astrophysics at Swinburne University. And for his PhD, Wael developed a real-time AI-based FRB detection system. Pretty cool. He performed FRB searches using this newly refurbished Molonglo radio telescope that's near Canberra, Australia. And he found some, I think the first 5 FRBs from that facility, and that allowed detection to study the FRBs at very high time resolution. Wael just recently joined the SETI Institute to work on the Allen Telescope Array and perform new science with the instrument. And his research interests include fast radio bursts, pulsars, which are highly fast rotating neutron stars, instrumentation and machine learning, and AI. So he's joining us tonight from Hat Creek. And I'll go ahead and introduce our second guest now before Wael speaks, because I think it'll be an easier transition. So our second guest is Daniele Micheli, who was born in Rome in Italy, where he obtained his master's degree in astrophysics from La Sapienza University. And then he moved to the University of Amsterdam to observe and study pulsars and fast radio bursts. After he got his PhD, Daniele accepted a position at McGill University in Montreal to work with CHIME, which is an acronym that stands for Canadian Hydrogen Intensity Mapping Experiment Telescope. And now, that's a new Canadian radio telescope located in Penticton, British Columbia. And he received a Banting Fellowship to find and study these fast radio bursts with CHIME. And he's joining us tonight from Montreal. So Wael, I understand you're going to be the first speaker.
Yes. Thank you, Jill. Thank you for this opportunity to be able to talk about my research and talk about fast radio bursts. And I shall start by sharing my screen. I hope everyone can see the slide. Okay, so we've spoken a bit about fast radio bursts. Bill and Jill introduced this new term called fast radio burst. But what are fast radio bursts? The short answer to this question is that we do not know. The long answer is an interesting, very bright, super bright burst in the radio spectrum that we happen to pick up using our telescopes, and we still do not know what generates these signals. So I hope I'm not going to go into a lot into details here, but a fast radio burst would essentially look something like this. I hope everyone can see my cursor. So we've got frequency on the y-axis and time on the x-axis. Now, the characteristic of a fast radio burst is that it's a really bright signal that follows a frequency to the power -2 curve. So that curve, if we fit that curve, it's exactly frequency to the power -2. Now, this tells us something really important about the propagation about that signal. So this signal happens to be flowing through the intergalactic space. And as it moves through space, it gets delayed or it gets dispersed. So frequencies at, or higher frequencies arrive first at our telescopes compared to later frequencies. And here I can show a small animation of how this effect happens. So you can imagine a group of swimmers. So in a swimming race, the swimmer that has the highest energy will arrive first to the finish line. And the first fast radio bus was discovered using the Parkes radio telescope. So the Parkes radio telescope is this instrument here. It's a massive 64-meter dish located in Australia. And this was back in 2007. And up till now, we haven't yet solved their mystery. So we've been studying fast radio bursts for maybe more than 13 years now. And we've discovered maybe around 100. So, well, we still don't know what FRBs are, but what can we actually use them for? And this is a really important question. So if you go to the pie chart here, so that's the decomposition of how our universe, or how our universe is divided. So we see that there's 75% of the universe is dark matter, 21%, dark energy, 21% is dark matter, whereas 4% is the normal matter, which are the material that we can actually see with our telescopes, with our eyes. So everything we see in our universe, essentially galaxies and dust, is the 4% of the universe. Now, the shocking part is that half of that 4% or 50% of that 4% is invisible to us. And we theorize that this 50% might lie in a highly diluted version between galaxies. Now, FRBs, because they happen to be coming from outside the Milky Way and from literally halfway through the universe, they carry the imprint of this ionized medium. They carry the imprint of this missing matter. So FRBs can help us really understand this and help us weigh the universe, like literally weigh the universe. And as a last point I want to make here, so this is yours truly. This is the Molonglo radio telescope. It's a massive 1.4 meter, 1.4 kilometer telescope located next to Canberra. And this is where I've done my, or this is the instrument that I've used for my PhD. Molonglo is an interferometer. So here there are a distinction between, or two ways we can do radio astronomy essentially. Either we can build a really large single dish instrument, just like the Parkes radio telescope, or we can use an interferometer like the Molonglo radio telescope in order to find FRBs and search for FRBs. And on that note, I will let Daniele talk more about CHIME. And so off to you, Daniele.
Thank you, Well. So my name is Daniele Michilli, and I want to continue exploring this interesting topic that is fast radio burst. I hope that that my slide will be uploaded. Yes, thank you. So imagine that you look at the sky, but imagine that instead of seeing the usual visible light, you see radio waves. The sky would then look very different, and an image of what you will see is reported in the upper left part of your screen. For now, just ignore the vertical stripe in the middle. I'll discuss about that later. But just focus on the background. On this radio sky, you would see fast radio bursts as flashes of lights, very quick, lasting around a millisecond, appearing randomly in every direction, one every around 10 seconds. So this is a common phenomenon. And the way, we looked at these fast radio bursts for a long time, and we found that a few of them emitted multiple bursts, but the vast majority of them didn't. we still don't know if there are two populations of fast radio bursts, or we haven't observed long enough to see all of them repeat. And this is one of the open questions of fast radio bursts. How a telescope observe a fast radio burst or look for a fast radio burst? Imagine that a telescope look at a patch of this radio sky and monitors the signal strength of this patch of the sky. What you will see initially is just noise. If by chance you are lucky and a fast radio burst goes off in this patch of the sky that we call field of view of the telescope, then you will detect a spike, a peak in the strength of the signal that your telescope is measuring. And congratulations, you will have discovered your first fast radio burst. This is exactly what astronomers do. And after removing this dispersion effect that Wael described before, we can use the telescope to study the time and frequency properties of the burst. In the upper right part of the screen, you can see some examples of this waterfalls plot that Wael was describing before after removing the dispersion effect. These waterfalls represent a sort of fingerprints of the burst. They encode the information about the emission mechanism of fast radio burst, which is still a mystery. And we've never observed before this sort of patterns of the signal in time and frequency. So it's very important for us to find as many fast radio bursts as possible. And this is one of the reasons why astronomers started using more and more interferometers as compared to single dishes, as Wael described. In fact, while a single dish is usually very sensitive but can observe a tiny, tiny fraction of the sky, so the probability that a fast radio burst by chance happens in that specific space is very little. So you will observe only one fast radio burst every weeks or months of observations. With an interferometer on the other side, that is a telescope formed by many antennas, you can observe many patches of the sky at the same time, greatly enhance the number of fast radio bursts that you can detect. One of such interferometers is the CHIME telescope, and this is the telescope that I'm using in my research. You can see a picture of the telescope in the bottom panel, and it is formed by 4 half pipes. It is in total 100 meters long and 80 meters wide, and you can see a person standing on top of the telescope if you squint your eyes for size comparison. Originally, it was designed for a completely different purpose. It was a cosmology experiment, but it was soon understood that its very large field of view could allow us to detect many, many fast radio bursts. This is a perfect hunting machine for fast radio bursts. It is formed by more than 1,000 single antennas, and they are correlated together to look more than 1,000 patches of sky simultaneously. You can see a representation of these patches on the sky that through which the telescope sees the fast radio burst in the upper left plot. They are represented as the dots in the vertical stripe at the middle that I was mentioning before. And every time a fast radio burst goes off in any one of these 1,000 places on the sky, we detect it. The data generated by these 1,024 antennas is huge, so we cannot store all of it. We developed some automated software based on artificial intelligence that continuously monitor the sky, and if there is a signal resembling a fast radio burst, it stores a few seconds of data around the burst. My project is to take this data and improve the characteristics of the telescope to study the signal at the maximum possible resolution, and even localizing fast radio bursts to parts of the sky, trying to determine which galaxy they come from. And with this, I give the ball back to Jill.
Okay, thank you very much, both of you, for those short summaries. And I'd like to remind people that you can use the Q&A feature at the bottom of the screen to send questions for the two speakers, and we'll get them answered towards the end of the session. And from looking at the chat, I'm getting a lot of remarks about people are having some trouble with their screens and are not seeing what we're seeing here, because it's working very well for the panelists. And I know that Lily is trying to work on that. But I think we're going to forge ahead anyway. So, you know, in astronomy, we have this really robust history that we go and we argue for funds to build a telescope, a new instrument, because it's going to solve all these questions that we know about, right? And luckily, we've had the experience that the new instrument, yeah, it usually does answer the questions, but it also shows us something that we didn't expect at all, right? Just because we're looking at the universe in a different, new way. And that's the story with the FRBs, right? Parkes built a 13-beam receiver for their telescope so they could more efficiently search for pulsars, and it worked beautifully well. And then there was a bunch of data that was taken in 2001 that was sitting in a large database. And in 2007, Duncan Lorimer came along with a lot more compute capacity than had been available in the earlier time. And he was able to search that database deeper, go to a larger range of dispersion measures and with higher time resolution. And then he discovered this Lorimer burst, or the first fast radio burst. And I think that it's just one of the great things about doing astronomy and looking at the sky in new ways. So what I'd like to ask both of you is, in your opinion, right now, what's the hardest technical challenge of detecting more FRBs?
I can go first if Danielle. Yeah. Our radio sky is heavily polluted with communication devices and communication services. And this is fine. We need satellites and we need to use cell phones. We need to use
not at Hat Creek, you don't.
Not at Hat Creek, no, thankfully. But the very spectrum that we use to discover FRBs from a radio astronomer perspective is heavily polluted by other communication emission sources and satellites. So I would say one of the hardest, or one of the biggest challenges in radio astronomy right now is being able to search the data effectively and not be deceived by the interference signal. So colloquially, we call interference RFI, which stands for radio frequency interference. And this is why we need to develop machine learning algorithms or AI algorithms that would sift through the data and make sure we find interesting signals rather than interference. So that's my answer to that.
Okay, and let me ask you, since you started down that route, these AI algorithms that you're building, are you training them on a particular pattern, or can they work well enough to tell you that there's something there other than noise and show you a pattern that you didn't expect and maybe find a SETI signal instead?
Yeah, that's an interesting question, Jill. Thanks for that. There are a few ways we can do this. We have different kinds of machine learning algorithms or AI algorithms. One of them is called the supervised AI, which essentially means that we have a bunch of data. We feed that data to the algorithm, and we say, find something similar. Unsupervised machine learning algorithms, so that's the other type of AI algorithms, is called the unsupervised. Essentially, we say, okay, this is the typical type of data that I see. If you see something else, please let me know about it, or something atypical, please let me know about it. Well, what I've done recently is using supervised machine learning algorithms, because these are a bit easier to train and a bit easier to deal with. But having unsupervised machine learning techniques, which are being developed by other researchers, are also being deployed on a daily, and they are being developed and deployed progressively.
And Daniele, Chime is turning out to be such a spectacular instrument for this purposes. So dealing with all that data, what's your answer to the question about what's the hardest technical challenge to finding more FRBs, or if you've already solved it?
No, well, first, I very much agree with Wael, but also you partially answer in the question itself. Like, dealing with the data is the challenge. A telescope like Chime generates an amount of data that is comparable to like the largest websites in the world. And we are building machines with even more antennas and more collecting area. So dealing with all this data is really a technical challenge in itself, and even more so storing the data and analyzing all the data. Until a few years back, you could basically go through the candidates of your telescope and check all of them by eyes. But as it was mentioned, it's not possible anymore. So you need automatic programs, and you raise a very good point. Are these automatic programs only finding what you expect them to? That is a real challenge. I think that unsupervised machine learning helps, but I also think that as astronomers, we always should look at the rawest possible data from time to time. It's not possible to look at hours and hours of data because it's too much, but maybe just selecting, a few seconds every month and taking the time to really check it. I think it's a good exercise that everybody should perform with their instruments.
So I was struck by looking at your slides that there's a certain resemblance between Molonglo and Chime. Is there indeed any history that connects those two?
I am not aware of, I don't think Chime was directly inspired to Molonglo, to my knowledge. But, Molonglo is a pretty old design that was refreshed a few years back. And then we switched to large single dishes because they were easier to use and very sensitive. And then we're going back to these interferometers now that we have the computers to like use them at their full capabilities. So yeah, it's fun, circle of life that comes back.
Okay. So localization's a problem, right? And you are building outriggers for Chime to help you get more precise localization on the sky. But while wouldn't simultaneous observations from multiple sites be what you want here? Thinking about, we just spent something like 5,000 hours of VLBA time to get a good map of the galaxy. Is that not the kind of thing that you might want to do, or is just the field of view too small for these VLBA telescopes?
Yeah, we are running out of telescopes. We do not have enough telescopes to connect them all in a network and do FRB science with them. Of course, there are telescopes that are doing other kind of science, and we cannot really control all of them and use them at the same time for FRBs. But we are getting better at doing this. The multiple detections at multiple telescope sites would be a holy grail, because you can imagine doing a sort of a parallactic observation of the same. It's same as having two eyes at the same place, so we can actually localize better, and we can observe at different frequencies, for example. Yeah, I hope that answers the question, Jill.
Okay, yeah, well, we are always looking for more telescopes, right?
That's yeah.
So can one of you summarize for our viewers the different classes of possible explanations, the different models that we're thinking about to explain these FRBs? I mean, nobody has nailed it yet, but there are generally categories of theoretical explanations.
Sure, I can try an attempt.
Okay.
Before CHIME started, actually, there was the internal joke in the field that there were more theories than actual bursts. Now it's probably not true anymore, but there are still many models, and this is because we haven't had much data yet. So to confirm or disprove a theory, you need a lot of data. That's why we're trying to find more and more bursts. Some of the, I would say the majority of theories predict that these fast radio bursts are somehow related to neutron stars, either with magnetars, so neutron stars with very high magnetic fields, or some sort of pulsars on steroids that emit these giant pulses for some unknown reason. Then there are more exotic theories, like involving supermassive black holes, or even exotic objects like axion stars or cosmic strings. But I would say that, yeah, the main the theories that are more widely spread are rotate around neutron stars.
And what do these theories say about why some of them are one and done, apparently, and some of them repeat either erratically or now one regularly? What distinguishes those?
Well, the important difference is, of course, that if something repeats, means that the object that causes them, it's not destroyed in the process. It's for theories is challenged to produce such bright bursts. They are like millions of times more luminous than anything that we've seen in our galaxy at this time scale and wavelength. So if you destroy an object, it's easier somehow to release such a powerful explosion. I think that the right answer is that theorists are still divided on the subject. Some of them think that there could be two or even more different classes. Some of them try to theorize processes that we maybe haven't observed in our galaxy that enhance the luminosity of this burst. As an example that comes to my mind, for example, a magnetar, a neutron star with a very high magnetic field that I was describing before. We have a few in our galaxy that emits radio, but they are pretty old. What will happen if there is a newborn magnetar? Some theorists started to ask themselves, just to give you one of the many examples.
Well, do you have a favorite theory?
I love neutron stars, and I love smashing neutron stars together. So one of the theories out there is that, or one of the theories that predict non-repeating fast radio bursts is that neutron stars are spiral into destruction essentially, and then when they smash into each other at some point and they release energy. So to me, that would be this, the theory of my choice.
Okay. So early on, with just a handful of FRBs, there was a lot of discussion in the community about whether these were nearby, and therefore the dispersion measure, which is very large, indicated another source of electrons close to the object, or whether in fact they were at the distance that you would calculate from looking and essentially counting the number of electrons from here to the source with that dispersion measure, and then shaking their head because it implied that they were so powerful. What was it that finally convinced the community that, yes, those dispersion measures really do represent extragalactic sources?
Yeah, this is a big thing in the fast radio bus community, and I would want to add something on top of that. Is that fast radio bus were not the nature of the astrophysical nature of fast radio bursts were always being doubted by the community. So after Lorimer, Duncan Lorimer back in 2007 reported the first FRB, there was a big dispute in the community whether these FRBs were real to start with, because they implied this massive distance and or large distance and large energies. So back to your question, Jill. I think what solved the mystery of where FRBs are coming from. So again, with single dishes, we do not know where FRBs are coming from. We just see a single pixel on the sky or a few pixels in the sky. We can sort of know that it's coming from, you know, this small patch, but there are millions, maybe thousands of galaxies in there. So we do not know from where the FRBs are coming from. That question was only answered when FRBs were localized using interferometers. So when we discovered them using interferometers, we could produce an image on the sky with a really high spatial resolution. And we can tell from where the FRB was coming from. And then we can know which galaxy that the FRB was coming from. And then we can ask how far this galaxy is. And this is when we were sure that FRBs were extragalactic or cosmological, and that the dispersion measure or the signs that the dispersion measure was giving us was true, that these FRBs are actually cosmological. And this happened in the last 2 or 3 years.
Right.
Yeah.
And, but Daniele, we've done more than one localization. And are these FRBs coming from the same type of galaxy?
Yeah, that's a very good question. And actually goes back to your initial question, like what are the surprises in the field? With fast radio bursts, it's always a surprise. You expect something and they always surprises you. We now, I think, have almost 10 localizations, and they come from all kind of galaxies, all kind of environments. There are like close by galaxies, very far away galaxies, big galaxies, very small galaxies, dense galaxies, tenuous galaxies. So we were hoping initially that with a few localization we will have understood and observed their environment, and so, you know, analyze which kind of objects could live in such environments. But now the game is more difficult. We need to find, again, more and more fast radio bursts because because there are different environments, so you need to study all of them and try to find some common characteristic.
Okay, and so this is a little bit of a tangent, but would one of you try to explain what a Parroton is? And why is it that a microwave oven in the woodshed at Parks that provided a lot of false positives didn't in fact tarnish the reputation of FRBs? I mean, we worry about that in SETI all the time. We don't want to cry wolf because we figure If we do, and it turns out it's wrong, we'll never get another chance. But it didn't seem to bother the FRB research field. So would one of you want to take the question about Parrotons?
Should I do it, Daniele?
Well, you are the Australian.
Well, I'm not the Australian. At least I've spent the last 4 years in Australia. So yeah, so Parrotons were discovered after FRBs were discovered. Now let me just put the context here. So FRBs, or the Lorimer burst, was discovered in 2007. A few years after that, when we started really looking into the data and see if we can find any Lorimer burst-like signals, we ended up finding these so-called Parrotons. Now, Parrotons have a dispersion sweep, which resembles highly the Lorimer burst. But the only difference was that the Parrotons were seen in all of the beams of the multibeam. So again, we have the single dish, the Parkes radio telescope, and I think Jill touched upon the multi-beam receiver. So the multi-beam receiver is essentially having multiple eyes on the sky. Now, a signal that's coming from the near field of the instrument would light up all the beams at once. So we'll see the same signal in the 13 beams. That wouldn't be the case for an astrophysical source. So the Lorimer burst only appeared in a few beams because there's a response function of the beams, but it only appeared in a very small subset of the entire multi-beam, whereas Parrotons appeared in all of the beams at once. So this was we were a bit, let's say, lucky that we have this ability to distinguish between Parrotons and between fast radio burst, or between any astrophysical signal per se. Now, what generated Parrotons? Funny enough, it was microwave ovens. So if you do not wait for the microwave oven to switch off before opening the door, a discharge would basically release a bit of radio photons that are of course harmless, but they happen to swipe through our telescope, and then we pick them up. So Parrotons were concentrated around lunchtime and around dinner time. So that was also another distinction.
But it didn't hurt the field, right?
It did in the mainstream media, I would say it did, but we knew all along that these were non-astrophysical signals. Now, of course, the media picks up microwaves and radio telescopes, and and then they turn it upside down, and then they write a story about how we cannot distinguish between microwaves and astrophysical signals. But yeah, we knew all along that Parrotons were not astrophysical, but at the same time we needed to be careful about how we choose our we do not want to cry wolf, essentially, like you said.
Yeah. So I want to go back to the algorithms that you're using at either Malongolo or Chime, and what confuses those algorithms? And have you been able to stress the system, the algorithms, enough to figure out whether it's giving you false negatives as well as false positives?
We have tested this algorithm in many ways. One of them is to look at pulsars. So pulsars are the neutron stars that emit radio waves every now and then. We can pick that up and we can feed those signals to the algorithm and ask the algorithm, are you finding FRBs? Well, FRBs and pulsars sort of look the same, but pulsars have way smaller dispersion measures. So we can play this game, essentially. We can observe a few pulsars, feed them to the algorithm, and ask the algorithm if you find something. Another way we can do is to inject fake signals.
Mm-hmm.
So we go to our telescope. Well, we do not do it. We do it on the digital side, of course, but we write a small algorithm that would inject a small signal. And of course, we log it in order not to confuse ourselves. And we try and pick it up on the other side and see if we can find it. And if the algorithm finds it, then great, we're doing a good job. If we do not find this fake signal, then we're doing a bad job. So yeah, this is how we train, and this is how we evaluate our algorithms.
So Daniele, you're upgrading CHIME at the moment and putting in, as I understand it, sort of outriggers to get you better localization. What's the time scale for that?
I would say a few years. We received design funds from the Gordon and Betty Moore Foundation to build these outriggers, which are basically smaller version of the telescope distributed across North America. You were mentioning VLBI before, which is like this existing array of very big telescopes across the world. The problem, as you were saying, is that their field of view is extremely small. So two fast radio bars were localized with the VLBI system, but both of them are repeaters, which means that we knew that they were going to be active in that specific location of the sky. With CHIME, however, you have a very large field of view. So with the triggers, you can localize all of the hundreds of fast radio bars that you discover. So you go from having one localization maybe per year to one localization, I don't know, per week.
Okay.
And this should happen within a few years. As I said, the design already started.
And the outriggers will all be around Penticton, or you said North America?
North America. The location will still be decided, but there should be probably one in the US and at least a couple in Canada.
Oh, great, great. So actually what I'd like to do now is turn this over to Simon and Frank, who have been looking at the questions that our audience have been submitting, and I see 88 questions at the moment. I don't think we'll have time to answer all of those, but perhaps, Simon, you can gather them together in groups, and then I'd like to wrap up with one last question when we have to end the session.
Okay, well, Frank is going to, he has been helping me put the questions together, and he's going to pose the first one.
Yes, so we have a lot of questions on this topic. People are very interested in knowing the amount of energy that is typically released in FRB outburst. Roger asked this question typically, for instance, and also questions about what will happen if this kind of FRB happen nearby Earth. Can you give us an idea of the scale and the consequences?
Should I go, Daniele?
Sure, you want to take that?
Okay. So I can give you a number, but the number wouldn't make sense to the general public. I can make a small comparison. FRBs, if they are, well, we know already that they are cosmological, they are so far away. FRBs emit the energy worth of the sun's energy in 100 days in only 1 millisecond. And this is a lot of energy. Now, we haven't yet seen FRBs to emit in any other wavelength, so it's only emitting in radio. So if something happens in the Milky Way, which is highly unlikely again, because we can estimate sort of what is the rate of FRBs per galaxy, let's say, and this rate is around maybe once every 1 million years or something. So if something happened, or if an FRB source emitted a fast radio burst in our Milky Way that doesn't emit anything except radio photons, our communication devices might be harmed, of course, but nothing will happen. There wouldn't be a serious harm directly to us, of course. But again, this is highly unlikely, given that FRBs cannot, or the rate of FRBs is very small. And yeah, I guess that's.
In an individual galaxy, the rate is small, but can you give the audience an idea of how many there are going off somewhere on the sky every day?
Yeah, so we've been in this talk for about less than an hour. So I'd expect a few FRBs has whizzed by us by now. So the numbers are about a few thousand per sky per day at a certain sensitivity or at a certain brightness. So yeah, but there are a lot of galaxies out there. So this is why we can see, or we can estimate a few thousands per sky per day.
Okay, good. A question from Dave, referring back to radio wave mysteries of bygone decades, and that's quasars. Maybe just say a quick bit about what a quasar is and whether you think these two phenomena are related.
Well, I'm not a theorist myself, but quasars are basically supermassive black holes that we have detected at the center of galaxies. But in some of these supermassive black holes, there is material being, let's say, taken to the black hole. So stars and gas accrete to the black hole and start getting hotter and hotter while they get closer and closer to the supergiant black hole, and they start emitting a lot of radiation. These are among the brightest sources that we detect. And there are two main differences with the emission of fast radio bursts. The first one is that quasars emit for millions, billions of years. They are not a flash of light. And the second one is that they, it depends, but they usually emit all over the spectrum. There are like X-ray quasars and radio quasars, while fast radio bursts have only been detected in radio. So the two things could be connected, and it was thought for some time because the first repeater that we discovered was found in the vicinity of something that could look like a quasar, even though we are not sure. And so some theories started describing this. For example, an interaction between a neutron star and a quasar. What will happen in that case? It's possible that the neutron star will take some of the material from the black hole and start emitting huge amount of radiations, or the magnetic fields of the around the supermassive black hole itself could sometimes cross their lines and emit this fast radio burst. But again, these are only theories, so we still don't know.
Okay, thank you. We have some questions about the technology and the way to detect those FRBs in the future. One question's about is that have we been thinking already of starting building antennas on other planets, on the moon, around Earth, a network that will be able to detect those FRBs, or doing even a bigger network of radio telescope that will be able to pinpoint the exact location of those FRBs? This is a question for Vaishnav.
Yeah, we've been thinking a lot about designing new instruments, about building new instruments, and as you said, about sending satellite radio instruments into space. And on the moon, for example, there are a lot of plans to build telescopes on the moon. Of course, this is not going to happen in a year or two, but yes, getting us outside the Earth and all the communication services and all the light pollution, that would be great.
All right. Well, we're talking about technology. I think we need to switch to alien technology. Is there a possibility, Dave asks, whether these FRBs are signals from intelligent civilizations? How would we determine whether these are natural or artificial?
Well, this has been a question asked since the beginning, since the first fast radio burst was observed, and I can say with confidence that fast radio bursts look very different from what we would expect a signal from another civilization would appear. There are many differences. For example, fast radio bursts are relatively broadband. They are emitted in a broad spectrum of frequency, while you would expect communications from other civilizations to be narrowband. There are other similar differences, But I think that one of the most important is that some of these fast radio bursts have been found in places where life would be very difficult to be supported. Places with extreme magnetic fields, densities, pressures, and temperatures. And also the amount of energy that must go into generating these fast radio bursts, and the number of fast radio bursts that we detect every day are all things that then tends to distinguish these fast radio bursts from what we expect an alien civilization will produce.
But a signal where you had a negative dispersion would be a very good candidate.
Not really, Jill, in the sense that even an alien signal that travels through space, even that one, even if it's artificial, will be dispersed. Of course, if they think about it and they produce some, something mimic the dispersion to make us understanding that it's aliens, then yes, but
Well, what I was meaning is that a signal where the low frequencies arrive before the high frequencies, so dispersed in the other direction. We could make such a thing.
Yeah, exactly. You should, yeah. You make a signal like that, but after it travels through space, there will be the dispersion that align the signal and then disperse in the right sense again.
No, okay. I think
So
we get around that. But anyway.
That could be, but it depends how far away this
Yes.
civilization would be then.
Yeah.
So we have a lot of questions about potentially alien communication disguised into FRBs, of course, because we are the SETI Institute after all, right? One question we have here is that, is there anybody that search for any type of content in the signal, for instance, at very high frequency? Like we can see content in the signal sent to Earth, like music, news, videos, and so on. And could it be that those periodic FRBs are some kind of alien form of communication or spacecraft propulsion that we don't understand?
I can probably go for that. So the FRBs have really small duration. They're only a few milliseconds, and there's not much room to encode a lot of signals in 1 millisecond. I might be wrong here. Jill might know better about the subject, of course. But yeah, one of the theories actually is FRBs being light sails, being an extremely powerful laser that is, it's a technology actually that we are thinking about right now to send a small device into interstellar space. To accelerate this device, we use highly powerful lasers. So one of the theories describes artificial or alien civilizations sending light sails into space, and this is how we find FRBs, and this is how we find repeating FRBs, maybe. But yeah, again, this is all still theories because we have no clue yet. We have no proof for that.
Okay, just I know we're running out of time a little bit. The question on using machine learning and artificial intelligence on studying these. What are the potential successes and hazards of trying to get AI in helping you detect and decipher these?
Well, the success is, of course, that we are detecting these signals using artificial intelligence. This is not something in the future. This is already happening, and was actually one of the main subjects of Wild's PhD thesis. And the risk is, as we discussed before, is that we miss something unexpected. That's why I was suggesting that we should always take the time to look a bit of of data before the artificial intelligence selects it for us. It's not possible to look all of it. So artificial intelligence, it's a necessity. It's not something that we do for pleasure. It's because we have too much data to analyze. But again, trying to understand exactly what we should use that about, it's one of our jobs.
Hi, Jill. I'm sure you have some questions too.
Well, now my question was, we have these wonderful speakers because of their expertise in FRBs, but they're young, right? They have long careers ahead of them. And so I would like to ask both of them to think about, if they controlled a large source of funding, right? What would each of you decide to build in order to explore the universe in a new way, a parameter space that hasn't been very well explored?
I feel that's similar to an interview, like a job interview question. So this is a typical job interview question. But yeah, I mean, I am a bit stressed for that. No, okay. Having a infinite amount of funding to do science with fast radio bursts, I would say building many more dishes with special kind of feeds that would allow us to observe bigger and bigger observing bands. So essentially having a bigger and bigger observing bands. And of course, by the necessary computing needs to analyze the data. So building more telescopes with a higher frequency observing capability, and computers and facilities to analyze the data.
Seems like we should finish the ATA.
Yeah.
We were going to build 350 dishes originally.
Let's hope for that.
How about you, Danielle? Any other parameter space, maybe not having to deal with FRBs, but just something where we might once again get surprised by what's out there?
Yeah, yeah, there are many parameters that we haven't searched yet. Something that will require a lot of funding, and while was describing before, is going into space with radio. We are already into space with X-rays, but since wavelengths of radio are longer, we need bigger instruments, and bringing a bigger instrument to space is more expensive. That's one of the reasons we haven't done that yet. There is one exception. Last year, a very small antenna has been developed on the moon as a small research project. And this I think will be a very nice thing to do for the years to come. But this is very much in the future. Something closer that we could do right now is, for example, extending the parameter space in time. We were mentioning that we take images of the sky, but these images have a duration down to a couple of seconds. While searching for fast radio bars, we go up to a few tenths of a second. So right there is, for example, a parameter space that is quite unexplored in radio. What happens around timescales of 1 second? And this is only speaking about the radio. If we go, for example, to optical, there are like instruments that are being built to try covering similar parameter spaces and going around same directions. And yeah.
Okay. Well, in optical SETI, there are 2 instruments that are being built that will take us from nanoseconds to second timescales. We're trying to figure out how to look at all the sky all the time. So maybe we will be surprised, or maybe we will find what we built the instrument to find. So I think at this point, given the clock, we need to bring Bill back in to thank all of you. It was very fun for me to talk with you tonight.
Wonderful. Well, thank you, Jill. And hello, Jack. Nice to see you there. Great to have you joining us tonight. And to Daniela and to YL, thanks so much for your sharing your knowledge and expertise in this amazing area. Fascinating topic. And of course, it raises all kinds of follow-on questions. It's like everything else, especially in somehow astronomy. The more we know, the more questions we have, and the more we learn, the more curious we are. It was great to have so many people from all over the world joining us tonight. I counted, I don't know, 15 or more countries and about 25, 26 different states and all over California. So thank you so much for joining us. We got tons of great questions, obviously more than we could answer. Since we're a nonprofit, if you send us tons and tons of money, we will pay our panelists tonight extra to answer as many of those questions as we possibly can. So, you know, keep that in mind. That's always an option. But wonderful questions, really very insightful and very interesting. Great answers from our panelists. And of course, thanks to our team behind the scenes, you know, Jasmine and Lee and Simon and Rebecca who make this possible. And of course, mostly thanks to all of you joining us from all over the world, and of course also our Facebook friends. So while we were having this Zoom meeting, we were also live streaming on Facebook, which is fun. So we were able to reach even more people. It looks like we'll be doing this again next month, folks. So we'll get everybody informed as to what we'll be talking about for the May SETI talk. We hope you'll come back and tell your friends and bring them along as well. These are really wonderful. And I agree with many of the comments that have come in tonight, just how great it is that we're able to, as a result of the situation we're all in, share these talks with a live audience from around the world, which normally is just not been possible for us to do. So thank you again, everybody, for joining. Thank you to Jill. Thanks to our panelists and team. And from somewhere in Northern California, not at the SETI Institute, I bid you all a good night. I wish everybody good health, stay safe, be smart and responsible, and we'll get past this COVID situation and be back together again soon. Thanks for joining us. Take care, everybody, and good night.
Bye.
Bye-bye.